So let's try to absorb the ideas we got from the activity a little better. We can generalize the ideas that we saw in this activity. If f is a continuous decreasing function and the terms of our series are given by the function evaluated at positive integers, then we have this partial sum for our series, and we can look at it as a left-hand Riemann sum. So remind yourself here what's going on. Oops. Let's do this. For this here, this is a left approximation of the area under this curve, right? Because we're always, in each subinterval, we're using the left endpoint to evaluate the function and get the height of that rectangle. Okay, so this is a left-hand Riemann sum of f of x. That's what we mean by that. Okay. Since f is decreasing, we have that the partial sum is going to be bigger than the integral from 1 to n of f of x dx. This is kind of formalizing with math notation the observations we made in the previous activity. When we let n go to infinity, this relationship will still hold. So if the improper integral diverges, so does the series with the related terms. So this is what I was talking about earlier. We're going to talk next about this point I was making during the activity, that you don't always have to pick the left Riemann sum. It depends on what your purpose is. Okay, if we take a look at the right-hand Riemann sums, so notice what we have here is the right approximation of the area under this curve, because for each subinterval we're taking the right endpoint and evaluating the function at that point to give us the height of the rectangle. So if we look at the right-hand Riemann sums, then we have that the integral is now bigger than the series. If we notice here consistently, the rectangles, which represent the partial sum, the rectangles are shorter. They amount to less than the area under this curve. In other words, we're going to have some area missing, right? We have this area missing, we have this area missing, so the integral will be more than this partial sum. Okay, so here in this picture, the integral is bigger than the partial sum, and when we let n go to infinity, that pattern is going to be consistent, so it'll be the improper integral is greater than the series. So if we know that the improper integral converges, meaning this area under the curve as we go out forever and ever to the right, if that area is a finite area, then something less than that will also end up being finite in the limit. So to sum it up, the integral test tells us. Now at this point, before I talk about what the integral test says, it's important to notice you're not going to have to actually do this part anymore. This is to give you an idea of why it's true. The integral test itself is saying, okay, let's say you have a real valued function f that's decreasing and positive for all x larger than some number c. We don't care what happens before this number c, as long as eventually when you go out forever and ever, it's decreasing and positive. And suppose that a sub k, you have this sequence from which we're going to build a series, is equal to f of k for each positive integer k. In other words, we have this relationship where the terms of the sequence that build the series are each function values of this function. So the integral test says if the improper integral, which is the integral from c to infinity of f of x, converges, then the series k equals 1 to infinity of a sub k converges. That's thinking of this picture. But again, we won't need to make this picture again. We just need this fact. If the improper integral from c to infinity of f of x diverges, then the series diverges. In other words, if this area under the curve is going off to infinity, then the part sticking out above it is also going to go off to infinity, which means the series is going to diverge. Okay. We have a very important bunch of series, an important family of series that you're going to use for a lot of other things. It's very foundational. So we're going to kind of generalize some observations. We did the improper integral of 1 over k. What if we do the improper integral of 1 over k to the p, where p is some number? So in this activity, what you're doing is you're doing kind of a review of improper integrals. You're trying improper integrals with different conditions, and you're seeing what patterns you notice. If you haven't given this activity a try, please pause the video and do so now. Okay. Hopefully you had a chance to try these improper integrals. Essentially, you're doing a review of improper integrals for this activity and trying to make some observations. But let's work this out together. So we have evaluate the improper integral from 1 to infinity of 1 over x squared dx. All right, let's work that out. So integral from 1 to infinity of 1 over x squared dx. That's limit as b approaches infinity of integral from 1 to b of 1 over x squared dx. Just to make things easier on myself, I'll write it as x to the negative second power. Then I don't forget to copy my limit as b approaches infinity part. The antiderivative of x to the negative 2 is going to be x to the negative 1 over negative 1. So this will be negative x to the negative 1 from 1 to b. And now what's going to happen is I plug in b and I get negative b to the negative 1 plus 1 to the negative 1. So cleaning up the notation to make it a little easier to work with, I have limit as b approaches infinity of 1 minus 1 over b. And that limit will be 1, since 1 over b goes to 0 as b goes to infinity. All right, this tells us that the integral converges, therefore the associated series converges. What if we consider integral from 1 to infinity of 1 over x to the p dx? And now we're just thinking of p as being some number greater than 1. So we're going to analyze this case, which is a slight generalization of part A. We now have integral from 1 to infinity of 1 over x to the p dx. Again, p is some number greater than 1. When we calculate this improper integral, we're going to keep in mind that what we have is an exponent negative p. So negative p is less than negative 1. It's more negative than negative 1. So when we add 1 to this, that number will still be negative. So we have the antiderivative will be x to the negative p plus 1 over negative p plus 1. Again, taking this inequality p greater than 1, if I multiply both sides by negative, I switch the direction of the inequality. If I add 1 to both sides, I get that negative p plus 1 is less than 0. Less than 0 means negative. All right, I'm going to evaluate this from 1 to b. I have b to the negative p plus 1 over negative p plus 1 minus 1 to the negative p plus 1 over negative p plus 1. Okay, fair enough. Remembering what I just said, which is that negative p plus 1 is a negative number in this case, I can put this b to the negative p plus 1 downstairs. Kind of like how here we had b to the negative 1 and we wrote it as 1 over b. So I'll do that. And what I'll have is, let me just factor out this 1 over negative p plus 1 from both terms. I'll have 1 over b to the 1 minus p minus 1 in parentheses here. Let me make that b look a little nicer. Okay, so what's the limit as b approaches infinity? Well, now we have 1 over b to some positive power, because 1 over p now is going to be positive. If negative p plus 1 is negative, then the opposite of that is positive. That 1 over b to a positive power, where that positive power is approaching, where the base is approaching infinity, we're going to get 0 for this part. And so our final answer for the limit is negative 1 over negative p plus 1. Or we could also say it's 1 over 1 minus p. Now what about the case where p is less than 1? So we've already done p equals 1. We did that earlier. That was the harmonic series. We found out it diverges. We did one example with p greater than 1, and then we generalized it, and we found that when p is greater than 1, this integral converges, which means this series, which again we call this type of series a p-series, the p-series converges when p is greater than 1. So far we know it diverges when p equals 1, we know it converges for p greater than 1. So what does it do when p is less than 1? Let's work it out. We're going to calculate the integral from 1 to infinity of 1 over x to the p dx. We're going to operate under the assumption that p is less than 1. And we'll do the same setup we did the other times. I'm going to write 1 over x to the p as x to the negative p. So recall that if p is less than 1, that means negative p is greater than negative 1. And we know we're about to add 1 to that exponent because we're going to apply the antiderivative power rule, which means we're going to get that negative p plus 1 is greater than 0. In other words, the new exponent is going to be positive. that negative p plus 1 is now a positive number. I'm plugging in 1 to b. So I have limit as b approaches infinity of b to the negative p plus 1 over negative p plus 1 minus 1 to the negative p plus 1 over negative p plus 1. Remembering that negative p plus 1 is now positive in this case because we're making the assumption that p is less than 1 for this part C. Okay, so what does this mean? Well, let me just factor out this constant over here from the limit. So I have 1 over negative p plus 1 times the limit as b goes to infinity of b to the negative p plus 1 minus 1. Question now is, what is this limit? When you let b go to infinity and b is being raised to a positive power, then that quantity is going to go off to infinity. So this whole thing is going to end up being infinity. So that tells us the integral diverges, which tells us that the series associated with it will diverge. Okay, so to sum this up, the important example of the p-series, the p-series, k equals 1 to infinity of 1 over k to the p, converges if and only if p is greater than 1.